Section 6.3, the intermediate value theorem. Exercise 6.33. Let p of x be an odd degree polynomial function, and we mean with real coefficients. Prove that p of x equals 0 has at least one real solution. So this is sort of a cousin of the fundamental theorem of algebra, which says that for any polynomial function with complex coefficients, potentially, there is at least one complex solution. Okay, so that one's a bit harder to prove, but this one we can do without too much work. And it's going to rely on the intermediate value theorem, which says that if we have a continuous function, we have some value s between the images of the two endpoints of this interval domain, then there exists some c in that domain which maps to this value s. Okay. So how are we going to do this? Well, let's write out what our odd degree polynomial is. So n is odd, and if this is degree n, then the leading coefficient is non-zero. And just to simplify our lives a little bit, notice that p of x has the same zeros as negative p of x does. And so we can assume that this leading coefficient is actually positive. Okay. If it's negative, then let's just look at negative p of x instead, and then it'll be positive. Have the same zeros. Okay, well, to show that p of x has a zero somewhere, by the intermediate value theorem, it's enough to show that it has a positive value somewhere and a negative value somewhere else, because somewhere in between those two x values, so you're going to have to cross the axis, right? It's going to have a value of 0. So we need to show it's positive somewhere or negative somewhere. Okay, well, as long as x is not equal to 0, which is almost always true, we can write p of x in this form. And all I've done is factor out x to the n from every term. Okay. And well, the reason I've done that is we know exactly what the sign of x to the n is. Right? If x is positive, it's positive. If x is negative, then because n is odd, x to the n is negative as well. And so we just need to get a handle on the sign of the stuff in parentheses here. And it looks like kind of a mess, but the thing is, as the absolute value of x gets big enough, these denominators keep getting bigger and bigger and bigger, but this term, nothing happens to it, right? And so, yeah, if the absolute value of x is big enough, then none of these terms are going to matter. And an, which we're assuming is positive, is going to win, right? And so this value in parentheses will be positive. Okay. So to sort of force that to happen, what we're really looking for is for the absolute value of this sum here, of all the terms with an x in the denominator, to be smaller than a sub n. So that when we subtract, so that when we add it on here, it can only diminish the value of a sub n by at most a sub n, and therefore the overall sum will still be positive. Okay, so what is the absolute value of all of these terms? Well, by the triangle inequality, it's less than or equal to the sum of the absolute values of the terms. And I want that sum to be less than a sub n. Okay, and so one way to do that is to force all n of these terms to be less than 1/n of a sub n. And I accomplished that by making sure x is big enough. Okay, so if you just sort of see what it means for this absolute value here to be less than a sub n over n, you would get that absolute value of x is bigger than n over a sub n times absolute value of a sub n minus 1. And similarly, you get an inequality for each of those. And okay, we want all of those inequalities to be true, so we need absolute value of x to be greater than all n of those numbers. Okay, but that's just a finite set of numbers, so just take the biggest one and let absolute value of x be bigger than that. And we get that the absolute value of the sum is, if you string it together, it's less than a sub n. Okay. So then if we add on a sub n here, then by, well, sort of a rearranged triangle inequality, that sum is, well, the smallest it could be is if all of these terms were negative, right, and then that would be the same as minus the absolute value of all those terms. Okay. But we've just shown this absolute value is less than a sub n, so when you subtract it away, the result is greater than what you would get by subtracting a sub n. And a sub n minus a sub n is 0. So as desired, the sum, which was what was in parentheses up here, is positive. Okay. Well then, like I mentioned, if x is positive, then x to the n is, and so we have a positive times positive is positive. So we found an x value, actually lots of x values where p is positive. And if such an x is negative, then x to the n is negative, since n is odd. And so we have a negative times a positive, which is negative. So we found a bunch of x values where p of x is negative. And that should do it. Okay, so I mean, basically, if you take a step back and think about what the graphs of polynomials look like, you know that odd degree polynomials, if they have a positive leading coefficient, then they do always go off to positive infinity on the right and negative infinity on the left. Okay, so that's basically what we've shown.